In order to check where the curve is concave up or where concave down, we need to know the second derivative of y with respect to x. And again, apply the chain rule to the tangent. So we have this relation, d over dt of dy over dx, and all divided by dx over dt. From above computation, we know that d, this one, right? Let us compute it together. Okay. Here, let us take a closer look at the numerator here. d over dt, let us simplify this fraction, right? So 3t squared minus 3 divided by 2t. We can write it as 3/2 of, what is it? We break it into two fractions. Let us do it this way. So if we take this guy divided by this, right? We have 3t over 2. And then this guy, it will be negative 3 over 2, this guy, right? And the denominator is 2t. Okay? Now, this guy becomes easier. Derivative of this guy and derivative of this guy. Okay? What is it? Times 1, right? d over dt of t is 1. And this here, 3 over 2, derivative of 1 over t give us? Okay. Here, to answer the question of Aluk here, look at this guy. This is negative 3 divided by 2t, right? Let us write it here. Divided by 2t, this is a product in the denominator. We can write it as 3 times 1 divided by 2 times t, right? And properties of fractions, division and stuff, we know that it is the same as negative 3 over 2 times 1 over t. They're the same thing. Okay. Are we good, Aluk? Does it answer your question? For t squared, for 3t squared here, divided by 2t here, right? T will cancel with t, which give us 3 over 2 t, right? Is that okay? Just simplify it, yes. About everyone, is it clear this part from here to here? Just simplify this fraction. The reason we simplify it is that now we deal with two simple things, okay? And derivative, this is a constant. Derivative of 1 over t is simply a quotient, 1 over t, right? And what is it? Yes, be careful with a negative sign. Negative 1 over apply the quotient rule, right? Very good. Thank you, Victoria. How about everyone? Are we good? So, therefore, and the denominator here is 2t. Just rewrite it. So again, the same story. This is a number divided by 2t, right? And what do we have if we 3/2 divided by 2t? What is it? Yes, 3/40. And this guy, or yeah, it's up to you. There are many ways. Minus will give us plus. Here, this guy, it will be 3/4t cubed, right? This is one way, or you can do it this way. From here to here, in the numerators, 3/2 here is the common terms, right? Therefore, we can factor it out. Inside it will be 1 plus 1/t squared, right? Divided by 2t. Okay? They're the same. Just can we simplify it further? We can continue from either here or here. If we start here, we see that this numerator has 40, this has 40 cubed, right? So we can multiply t squared here, both sides. And anyways, it will give the same result. It will be 3/4 of t squared plus 1 divided by t cubed here. Okay? Just some algebra. You can double check it yourself. So, is it clear up to this point? Okay. This is the second derivative. Let me remind you. If we're given the function fx here, and if the second derivative of this is positive, what does it mean? Yes. Right? Let's say it's on an interval E. And if second derivative of this is negative on the interval I here, then it will be, yes, concave down on I, sorry, here, okay? So we have these properties. And what we found here is the second derivative of these curves, right? (3/4 of t squared plus 1 t cubed. In order to study the concave up and concave down properties of this guy, the easiest way is to make a table like we've done this yesterday. So let us consider the values of t, right? And t has the value from negative infinity to infinity, okay? And we want to study this second derivative. And look at this. This fraction is a quotient of two functions. The first one is a quadratic function here. And the second one is a cubic function here, right? So, therefore, if we know the properties of t squared plus 1, right? T squared plus 1, for any value of t, it is always positive, right? Or specifically, it's always larger than 1, because t squared is larger than 0 already. And here, when t is equal to 0, when t is equal to 0, and here is the second derivative of this curve here, when t is equal to 0, how does the second derivative behave? It's undefined, right? The denominator is equal to 0 is undefined, so we don't know. So we use this notation, okay? Let us just remove the values of these guys here. But now, t cubed is a cubed function. If t is smaller than 0, then t cubed will be negative. Thank you. It will be negative. Thank you, Camden and everyone. How about if t is positive? Yes, positive. Good job. So now, the second derivative is this fraction, right? So, therefore, we see that in this interval, it will be the division of a positive number divided by a negative number. Therefore, it should be negative. Very good. And here, positive. Okay, very well. Here, this guy, and the second derivative will be these multiplied with a positive function, a positive number 3/4 here. It does not affect the sign of these. Therefore, in short, we see that in this intervals, the function will be concave downward, yes. And in this interval, it will be concave upward, yes. Okay, that's it for this question. Very good. And then we should sketch the curve, right? Now, in order to sketch the curve, and we combine all we have, we know that the point at 3, 0 here. So we have the graph already, so we can save a little more time. Right here, the point 3, 0 is right here, right? As we have discussed yesterday, there are two tangent lines at this point. The first one has a slope of square root of 3. The second one is negative square root of 3 here, right? And t, so the intervals when t, go back to the notes. You see that when t increase, right? It will start from this, reach this point, and it will go up to this point, go back here this way. You plot these properties. And in the question B, we know that the horizontal tangent appear at 2 points, right? When t is equal to -1 or t is equal to 1 right here. Makes sense, right? And here is when t has a vertical tangent at this point right here, when t is equal to 0, right? This point. So it makes sense. And we have already studied the curve properties of the curves here. We've say that the curve is always on the right side of the OX coordinate here, right? From this part. Makes sense. Is agree with what we have studied yesterday. So do you have any question about this one? Very good. Thank you. So let us continue. There are some more parts here. Today we need to cover the area of the curves here. So if the curves y is f of x from a to b, then properties of the integral of this function from a to b will give us the area of the curves, right? Under the curve with the limits and the x-axis, providing that f of x is positive. The similar story. So if the curve is traced out once by the parametric equation, x is f of t and y is g of t here. And t takes the value from alpha to beta here. So in order to compute the area of the curves, it could be computed this way. Okay. Look at this. If x is a function of ft here, right? A function of t, then we see that dx over dt, what is it? It is the same as d over dt of the function fx, right? Or sometimes we write it f prime of x. Do you agree? Therefore, dx will be f prime dt. Okay? That is why we have this guy. Dx, we can write it as the terms of f prime dt. And y is a function of t here. It's similar to making a change of variable, right? Previously, we used the variable x, and now we can use it as a variable of t. It is a definite integral. So therefore, we also need to change the limit. And the limit, when a lower limit is the corresponding values of alpha here, and b will becomes beta here. That is why we have this formula. Okay? Or if the curve is negative, because we know area is always positive, right? That is why it could be from beta to alpha. Okay? But the terms here will be the same. Now, let us take a look at this example. We want to compute the area of this cycloid here. Okay. Now, according to this formula, A will be computed as integral from, we know that this cycloid will take the value from theta is equal to 0 to this point, right? If we write it in terms of x, it would be integral from 0 to 2 pi r y dx. Okay, that is when we will write it in terms of x. And how about if we write it in terms of y, of t? Oh, okay, anyway. In the previous question, we forgot. It's fine, let us continue here. Because I forgot mentioning one part in the previous question, but just keep moving on here. So here, if we write it in terms of the angle theta, right? D theta. We need to use this formula, right? Which is R1 minus cosine theta. Okay? Or let us write it slowly. Let us write it like g of t here. And f prime of g of theta. F prime of theta. And now the variable is theta. And theta of this cycloid will run from 0 to 2 pi, right? Okay? From this one. 2 pi because the cycloid is a point on this circle, right? It starts here. And when we rotate that circle, it will create this curve. And when it finishes one round, right? Go back to the original point. I mean, the point P here, suppose it is right here. It touched the line. It roll one round and it touch a line again. That is one. At this, it finished one round from 0 to 2 pi. Okay, that is the angle theta. And the distance or this line from here to here will be exactly the same as the circumference of this circle. And the circumference of this circle will be 2 pi times r here, right? That is the distance here. Okay, very good. Then what we need to do is to compute f prime of theta, right? Which is derivative of this guy over d theta, right? And what is it? Now, when we take derivative with respect to theta, r is simply a number, right? Does not affect to this guy. Therefore, we have r times, what is it? Yes. And? Yes, derivative of sine gives us cosine, right? Minus cosine theta here. Very good. Thank you, Jacob. So is it clear to everyone? Okay. Then, so we have everything, right? Now, let us plug it into this formula. Therefore, it will be the integral from 0 to 2 pi g theta, which is r1 minus cosine theta here times f prime d theta, which is r1 minus cosine theta again d theta. Okay. Is it clear? Okay, now it becomes an integral of a simple integration. This guy, how can we solve it? This guy and this guy, simply a number, right? You can take it out of the integration. Therefore, we can write it as r squared times integral from 0 to 2 pi. Okay. How about this guy? And this guy? This is 1 minus theta, cosine theta, perfect square of this, right? If we have this integral, how can we solve it? Substitution, then it will becomes very complicated. How about we explain this perfect square out and see? Okay. If we expand it, if we do substitution, and it doesn't help here, but let us try to expand it. A minus b squared will be a squared, which is minus, yes, 2 cosine theta, right? Plus the second one squared, which is cosine theta square here, d theta. Okay? Then this guy is a number, it's easy, right? This integral of cosine theta is also easy. How about this guy, cosine squared? Which formula should we use? Yes. It will be 1/2 double angle formula, right? Okay. Double check it if it is correct or not. So I believe it's correct here. So it will be integral of this guy, right? Let us write it this way. We find antiderivative of this guy. What is antiderivative of 1? Theta, very good. Antiderivative of negative cosine, 2 cosine theta. Very good, thank you, Camden. And the constant here, right? What is it? Yes, theta. And here? Is it correct here? Is it correct? When we take derivative of sine of 2 theta, it will be 2 times cosine of 2 theta, right? But in our case, the parameter is 1, therefore it should be like this, right? Or you can do a substitution, but it takes a little more time. Okay, now let us simplify it first. Theta plus here is 1/2 theta, right? Therefore, it will be 3/2 theta minus 2 sine theta plus 1/4 sine of 2 theta. Okay? And do it slowly. You will see that the final result will be 3 pi r squared. Go home and double check it. Okay? That is how we compute an area of a parametric equation. So, do you have any question up to this point? Okay, very good. And I wanted to do another example, but we don't have much time, so let us just move on here. A similar things. Now, we will study a new concept here. Now suppose, look at this. This curve, okay? If we want to compute the length of this curve S, imagine that we do the same technique with integration. We divide this guy into small parts, right? And each of these intervals here, it will be similar to, if we divide it very small, it will become a straight line, right? Close to a straight line. And let us call it ds. And if imagine here, a right angle corresponding to this small ds here, this direction is the x direction, so we call it dx here. And here is dy. Pythagorean theorem tells us that ds squared will be, yes, dx squared plus dy squared, right? Very good. So from this relation, we say that ds will be square root of dx squared plus dy squared, right? Now imagine this square root is the same as this one multiplied with 1, but we don't want to write it in terms of 1, we write it as dx divided by dx. Does it make any change? No, right? The same things. But if we do it this way, then now the trick is this. We bring this dx, we divide it by this guy, we can write it as square root of dx squared plus dy squared. Instead of writing dx here in the denominator, I can write it square root of dx squared, right? If dx and dy are positive. And the dx here, we just write it here. Okay? They're the same things, right? But now, the properties of division, right? The two positive thing under the square root, we see that it is the same as dx squared plus dy squared divided by dx squared, right? Okay, then keep simplifying it. We can write it as square root of dx squared divided by dx squared, we write it 1, plus dy squared divided by dx squared. Okay? Be careful. Don't be confused between this one and the second derivative. The second derivative of y with respect to x is written this way. But this one is dy, the infinitesimal change in the y direction. Dy squared divided by dx squared. Okay? Don't be confused with the second derivative, that's it. Okay? So anyway, in order to compute the length of the integral, the length of the curve from the points A to B here, it would be the integral from A to B of ds, right? Where each of the ds will be infinitesimal change here, right? And from above expression, we can write ds as in this terms, right? That is why we have this L curves to compute the length of the curve. Okay? From this, so suppose the parametric equation is x is ft, g is gt from alpha to beta of t in this interval. And the first derivative, dx over dt, is positive, we suppose. Okay? Then we can write this integral in terms of x. We can make a change of variable, so we can write it everything in terms of t. But now the lower limit corresponds to the value of alpha, and the upper limit b corresponds to the value beta here. So we write dx is this guy, right? Dx over dt, dt. Okay? You can imagine that dt and dt here cancel, right? Imagine that way. But actually, this guy is the first derivative of x with respect to t. And we can write, remember, yesterday we studied that dy over dx here is the same as dy over dt, dx over dt. Okay? It means that now, from now on, we can compute the line of the curves as, yeah, so do some algebra, read it yourself. The limit, the similar meanings with us Riemann sum. In short, we do some algebra. We have this formula to compute the curves, arc length of the curves here, using this formula. Okay. Here is f prime square. Here is g prime square from alpha to beta. Or, in short, everything is summarized in this theorem. Okay? Remember, dx squared is dx squared plus dy squared. We discussed previously. Now, let us apply this formula to this example. Here, find the length of one arc of the cycloid here. Okay, the cycloid is like this, right? Find one of these. Okay, the length here. We know that x is given by this, therefore we can compute dx over d theta. and dy over d theta. Okay? From this formula, it will be integral from alpha to beta of this square plus this square, or integral from 0 to 2 pi of square root of dx over d theta square plus dy over d theta square d theta, right? We are given here. So, and we found these two. We substitute everything into this formula. What do we have here? This guy square, it will be r squared times 1 minus cosine theta square plus what here? Okay. Are we comfortable with that? Very good. Then I think we still have time to do it together. Let us just try to do it. So therefore, okay, here, the like term in these will be this guy, right? R squared. Let us try to simplify it. We expand this perfect square. It would be 1 minus 2 cosine theta plus, yes, cosine theta square plus this guy here, right? Okay, I think we can stop here, go home, try to finish this, and see if you get the same result. Okay, I'll see you next week.